Alright, in this video we're going to take a look at finding a limit using a table. So a numerical method for finding a limit. So let's say we have the function f of x equals x squared minus 6x minus 7 all over x minus 7. So we want to find the limit as x approaches 7 of this function. Now if we plug a 7 in for the function, it's going to give us a 0 in the denominator. So again, limits don't care what happens at that value of x, they care about what happens as we get closer to it. So what we can do is we can plug in values of x that are very, very close to 7, both very, very close values that are very, very close less than 7, and values that are very, very close greater than 7. So again, f of 7 is going to give us an error message, but what happens, what's the behavior, the output behavior, if we plug in values of x that are really close to 7? So if we plug in 6.99, for instance, we get 7.99 in return. Getting closer to 7 for x, 6.999, we get 7.999 in return. And getting closer to plugging in 7 for x than that, we'll get a return value of 7.9999. So you might have a guess as to what value these numbers are getting closer to. So coming from above, values that are greater than 7, we have 7.01, we get 8.01. 7.001 is even closer to 7 than 7.01 is, and we get 8. That should be 8.001. I apologize for that. And 7.0001 gives us 8.0001. So the outputs coming from values below 7 and the outputs coming in from values higher than 7 seem to be getting closer and closer to an output of 8, and that's exactly what the limit as x approaches 7 of this function is 8. So as we plug in values that are closer and closer to 7, we're getting values that are closer and closer to 8 in return. So the limit of this function as x approaches 7 is 8. All right, example 2, we have f of x is 3x plus 5. We're going to find the limit as x approaches 2. So we'll start with 1.99, we get 10.97. Getting even closer to 2, 1.999, we get 10.997. And getting closer than that, we get an output value of 10.9997. So getting really close here to a certain number. So finding the limit as x approaches 2, what's the outputs? Well, let's see if we can have some outputs coming from values higher than 2. So like 2.01 gives us 11.03. 2.001 gives us 11.003, and 2.0001 gives us an output of 11.0003. So notice that these outputs are getting closer to a value as our x values are getting closer to 2. So from numbers below 2 and numbers above 2, they both seem to be getting closer to 11. So hopefully that was your guess for what the limit was as x approaches 2 of this function. All right, example 3, we have x cubed over 125 over x minus 5. We're going to find the limit as x approaches 5. So we're going to start with a number that is slightly smaller than 5, like 4.99. We get 74.8501. Even closer to 5, 4.999, we get 74.985001. And really close to 5 here, we get 74.9985. So it didn't have enough space in the calculator to hold all the decimal places. All right. Coming from above 5, we have plugging in 5.001, we get 75.0015. Even closer to that, we get this number here, a lot of zeros. And even closer to 5 than that, we get this number. So hopefully looking at these values here, what they're getting closer to and what these values are getting closer to, hopefully you can find out that the limit as x approaches 5 of this function is 75. All right, example 4, find the limit. Note that x is in radians. So we have the limit as x approaches 0 of sine of x over x, where x is in radians. If you take calculus, I guarantee you will see this limit. Again, you needed to find the derivative of the sine function when you first learn about derivatives. So you will see this again. But keep in mind that x is in radians. So we're getting closer to 0. So negative 0.001, here's our output value. Again, make sure you're in radian mode. Even closer to that, it couldn't hold that many decimal places, and even closer than that, still couldn't hold that many decimal places, so it just rounded it up to 1. Coming in from above, again, it couldn't hold that many decimal places, all those 9s after the decimal point, so hopefully you're looking at these values here. The limit as x approaches 0 of the sine of x over x is going to equal 1. Again, keep in mind, make sure you're in radian mode for typing this in. Alright, so in the previous examples, we found limits by evaluating values less than the value of a and also values greater than the value of a. Those are called left-hand limits and right-hand limits, respectively. So values that are less than that value of 0 that we're plugging in, those are your left hand, and values that are greater than 0, like we did going up this way, are your right hand. So your left hand and right hand limits. So going back to the very first example, that the values of x approach 7 from the left, so 6.99, 6.999, etc., our output values are approaching the limit of 8. So this is a left-hand limit for this function is 8. Likewise, the right-hand limit, as we get closer to 8 coming in from the right-hand side, our outputs are getting closer and closer to 8 as well. The notation for a left-hand limit, as x approaches a from the left, it looks like it's being raised to the negative sign power, but that's just a notation for as we approach the values of a from the left, or for values of x that are less than a. For the right-hand limit, it's the limit as x approaches a from the right is x approaches a, and it looks like it's to the positive power. But that's just notation for left and right-hand limit. And a two-sided limit, the limit as x approaches a of f of x is going to equal the limit, like we saw for the examples in this video, is going to imply that the left and right-hand limits are equal. And likewise, if the left and right-hand limits are equal, that implies that the limit as x approaches that value of a of the function is going to equal that limit value. So this we're going to see again with continuity, so we will see this relationship again in the future. Alright, that about does it for this video. In the next video, we're going to take a look at limits via graphs.